Hello, fellow explorers. Have you ever wondered, what's a slope field? Or, how do I find the value of a differential equation? Well, this week you'll get your answer as we delve into these and other universal secrets. Hello, and welcome back to Universal Secrets. This week we have a case of not only, but also, where we not only look at general and particular solutions, but also slope fields and Euler's method. Let's start first with the solutions. Differential equations are not exact values, but approximations of a value. In order to find the value of a differential function, it is necessary to find its solution. The solution is an equation set equal to y so that the derivative of y is equal to the derivative of f of x, or the derivative of the differential equation. The two types of solutions are general and particular. General solutions are obtained by finding the integral of a given function. Naturally, since most of the original values are not known, placeholders are inserted. Most of the time these placeholders are termed c, and can be labeled c sub 1 through c sub infinity, depending on what the case is. Some differential equations have singular solutions, in which the general solution cannot be written as a special case. General solutions also have order, which is determined by the highest exponential degree. General solutions of a first-degree differential equation represent the position and shape of graphs associated with the general solution. These curves are known as solution curves, or the curves that each solution graphs when certain values are used for the independent and dependent variables. The second type of solution, the particular solution, relies on initial conditions. Initial conditions include the value of a dependent variable, or one of its derivatives. Particular solutions differ from general solutions in that the goal of a particular solution is to find all the unknown values normally replaced with c's. By using substitution, the independent variable can be found and then manipulated to reveal the rest of the function after integration. Confused? No worries, let me explain. Say you're given the function s double prime of t equals negative 32. If you integrate that, you'll get s prime of t equals negative 32t plus c. Why? Because you have to multiply your initial constant by t, and you have to add c to account for all the numbers you don't know about before that. If you continue on, I'll get s of t equals negative 16t squared plus c1 plus c2. But that's just for general solutions. What about particular solutions? If we have initial conditions like s of 0 equals 80 and s prime of 0 equals 64, we can then plug those into the original function and arrive at the particular solution. S of t equals negative 16t squared plus 64t plus 80. Alright, adventurers, I hope you brought your helmets, because now it's time for slope fields. And we're going to need to go to outer space for that. I've got my handy-dandy space-time transmitter. Aha! See the lights? That means it's working! Ah, my friends, we've made it out here. Now we can look at the mysteries of the universe from the vantage point of the stars. But first, what's a slope field? That is a slope field. Collection of slopes among various points. While many problems can be solved multiple ways, it is sometimes impossible to solve differential equations analytically, when in this case, another method, such as solving graphically, is required. Slope fields are therefore quite useful in solving differential equations. This graphic method entails finding slopes at all points of a graph for given domains and ranges. Also called direction field, the purpose of these fields is to find the shape and position of differential equations by using the graph by way of connecting slopes in a logical and progressive pattern. Ultimately, once the graph is found, the area under the curve can be found as well, and also many other things can be found, such as rotational area. So slope fields are all well and good, but what can you use them for? Well, one of the most obvious uses of slope fields in modern science and mathematics is charting magnetic fields. All magnets and objects with magnetic properties have a magnetic field and exert magnetic forces on nearby objects. Whether or not the object will react to this force depends on if it is magnetically oriented or not. The easiest way to view these fields is to take any magnet and set it on a table with metal filings, as shown by the picture. The filings will arrange themselves in their current position to reflect the magnetic field. The fields are curved and thus have different slopes at different distances and positions in regard to the magnet. Magnetic fields are symmetrical about their poles, so while the example is only two-dimensional, the field is accurately represented by whichever plane is flush with the table. The Earth itself has a magnetic field, which protects its surface from cosmic radiation and solar flares. This field is thought to be generated by the Earth's rotation, which spins the Earth's core. The Earth's core is thought to be mostly composed of molten iron, which is a magnetically oriented substance. This produces the magnetic field when the iron is rapidly rotated, such as in a modern generator. The magnetic fields are often represented by the curved lines as seen in the picture above. Additionally, slope fields can be used in much the same way, since they represent curved lines as well, and different slopes at different points. Thus, slope fields can be used to calculate the area underneath these curves, and to monitor how the size of the field changes over time. Thus, scientists can monitor the size of the Earth's gravitational and magnetic field, and how it grows and shrinks, and how humans can ensure the longevity of the Earth's magnetic field. Whoa, that was some trip in outer space. Well, let's move on to the next topic, Euler's method. Other than the analytical and graphical methods mentioned earlier, there is also the numerical method. This means of finding the value of a differential equation, called Euler's method, usually pronounced Euler, but that's just a misnomer, approximates the differential equations in a similar way to particular solutions. Initial conditions are required for referencing a starting point with which to find the value of the differential equation. However, unlike particular solutions, the rest of the integrated expression is not found. Rather, Euler's method requires taking small steps along the tangent line defined by h until the point xy is reached. At this point, x equals the initial x plus h, and y equals the initial y plus h, times f of the initial x and the initial y. This means that Euler's method finds the points on the graph that are approximately equal to the exact solution. The larger the step sizes, or the larger the h, the fewer steps are required to reach each approximated point. However, each h that is smaller requires more steps and more time to reach the approximation point, but the end result is a more accurate reading. This method of finding the value of differential equations is useful when both analysis and graphing yield answers that are not easily estimated by eye, and provides more concrete approximation than just looking at a graph can give. So today we've talked about many different methods of finding differential equation values. For example, when attempting to solve differential equations, the three methods are readily available: using general and particular solutions to analytically find the value, which may or may not yield a rational value, graphing slope fields to estimate the value of a curve, and finally, applying Euler's method to numerically find the slopes at certain intervals. If one of these methods fails to give an accurate approximation, it's likely that at least one, if not both of the other methods, will yield a usable and logically appropriate value. Well, seems we're out of time for this week's Universal Secrets, so until next week, this is your host, Alexander McKnight, signing off. But before we go, I'd like to